Hello to my viewers. In today's session, we are going to discuss about resonance, rules of resonance, how to draw the resonating forms, and also we will cover up polarity of molecules. Hello everyone. Welcome to my channel, Chemistry by ANR. This is the topic that we need to discuss just after the topic we have discussed in the previous video. That is resonance structures. What is resonance? How are we supposed to see the resonating structures is of concern in this video. Now, resonance, we have seen that a single Lewis structure cannot often describe a molecule accurately. Like in case of ozone, I said that the O3 molecule has a different type of bond length. Let us see over here. When oxygen single bond was considered, the bond length is 148 picometer. For a double bond, it is 121. But this is the resonance hybrid that contains the contribution of both the structures. And in the resonance hybrid, both the oxygen bonds are equivalent. Both are having same bond length, and that is 128 picometer, which is in between 121 and 148, which I said attaining a partial double bond character. So, this type of process, the resonance, occurs when a structure cannot be represented, or rather I'll say a molecule cannot be represented by a single Lewis structure. A number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid, which describes the molecule accurately. And it is known as the resonance hybrid. Always remember, the energy of the resonance hybrid is lower than any of its canonical form. And the energy difference between the most stable canonical form, suppose I say there are A, B, C, D canonical forms of a particular resonance hybrid structure. Now, all canonical forms may not have equal contribution. The one which is more stable will have greater contribution than the one which is less stable. So, there are rules to see the stability that we will discuss later on, but the energy difference between the most stable canonical form, let it be this, the most stable canonical form and the resonance hybrid is known as resonance stabilization energy. That is the energy difference between the most stable canonical form and the resonance hybrid. Okay, moving on to the next, there is a problem which is explain the structure of CO3 minus, which is known as carbonate ion. This carbonate ion in terms of resonance. So you need to draw the resonating structures. You need to keep in mind that O3 minus means there are two negative charge over each oxygen atom. Out of the two oxygen atom will have the negative charge. So these are the possible canonical forms. These are the possible Lewis structures, Lewis forms. Explain the structure of CO2. CO2 molecule also, you need to explain it like this. These are the Lewis structures where you can have a neutral form. You can have a double bond shifted to either oxygen. If it is shifted to oxygen, then what is happening over here? One of the oxygen, it is getting a negative charge. The other oxygen gets a positive charge. Or it can happen on the other way. That means these two oxygens, at times it will have a positive charge, at times it will have a negative charge. So these are the canonical forms or the resonating forms. Now, resonance stabilizes the molecule, of course, wherever there is resonance possible, wherever there is more than one structure possible, the molecule attains extra stability, as the energy of the resonance hybrid is less than any of the canonical forms, which I have just now said. Resonance averages the bond characteristics as a whole, like the bond length we have seen between oxygen atoms in O3. So it almost has intermediate oxygen to oxygen bond length of a double bond and a single bond. Okay, so there are many misconceptions about resonating forms, but please keep in mind that the canonical forms, they don't have real existence, but they contribute to the resonance hybrid structure. There is no such equilibrium between the canonical forms. Only if there are identical canonical forms, then we can say they will have equal contribution. In the next leg of our discussion, we can see resonance structures from another study material. There we are seeing that certain substances can be represented by more than one Lewis structures, and these cases where more than one structures are possible are known as resonating structures or canonical forms, and they are represented by this double-headed arrow. It may be borne in mind that the actual structure does not oscillate between the resonating forms and it has its individual identity. Okay, so now the atoms that are forming the resonating forms, the electrons, they are guided by some rules. What are the rules? The contributing structures should have same arrangement of atoms. Arrangement of atoms should be same. They should differ only in electronic arrangements, the number of electrons, but total number of electrons will not vary. The contributing structures should have same number of paired and unpaired electron. That is what I was telling. The contributing structure should have nearly same energy, and the contributing structure should have a negative charge over more electronegative element and a positive charge over more electropositive element. That means if in case any atom or that is more electropositive gains a negative charge and an electronegative element gains a positive charge, that resonating structure or canonical form is considered to be less stable and less probable. Now, like the HCl molecule, they are telling that structure 3 is ruled out. Why? Because it is having a negative charge over electropositive and positive charge over electronegative element. Now remember one more thing, that wherever there is a charge separation, the canonical form is considered to be less stable. That means if in the same molecule there is a positive and negative charge, then the canonical form is considered to be less stable, like this. Now, if the canonical form has a positive charge over electronegative atom and a negative charge over electropositive atom, that is again less stable canonical form. Similarly, if two canonical forms are almost the same, identical, then those canonical forms are more stable because they have equal contribution to the resonance hybrid. Now over here, the structure 3 is again ruled out. Why? Because in the contributing structures, like charges should not reside on adjacent atoms. See, this is also positive, this is also positive. Nitrogen, oxygen, adjacent to each other, having same charge. So structure 3 is ruled out. This is not a probable canonical form. So resonating structures of some species, for practice it is being given. You can practice to see which is more stable. You have to follow the rules which I have already mentioned. Now these are NO3 minus, SO2, C6H6 benzene. You know, the structures of benzene, they are actually termed as Kekulé structure. Okay, Kekulé structure, and the pi cloud almost oscillates and each bond alternately becomes, see, this is once a double bond, in the next structure it gets a single bond. So each bond is having a partial I will say CC double bond character, and the bond length of carbon-carbon will be somewhat in between a carbon-carbon single bond and a carbon-carbon double bond. So So misconceptions we have seen in the previous study material. See the characteristics. The resonating structures are hypothetical. They do not have real existence. The actual molecule actually is what the resonance hybrid that we have already discussed. Bond length is intermediate. We have discussed. Resonance hybrid is more stable, having the least energy. We have discussed. The canonical forms may have similar energy, and the one which is more stable will have less energy, and the one which is less stable will have more energy. That also we have discussed. What is resonance stabilization energy or resonance energy? It is the difference between the resonance hybrid and the most contributing structure. That means the resonating structure that has least energy. That is known as resonance stabilization energy. Larger the value of the resonance energy, more will be the stability of the resonance hybrid. Now, calculation of bond order has a formula which we can apply to see what is the bond order. See this formula. Total number of bonds between two atoms in all resonating forms divided by total number of resonating forms. They have taken the example of carbonate ion, and these are the possible resonating structures, and as per the example they have taken this bond. See, it is what? It is total number of bonds between two atoms in all resonating forms. This carbon oxygen, here it is one bond, so 1. Here it is one bond, so again 1. Plus here it is 2 bond by plus 2. By total number of resonating form, there are 3 resonating forms, so by 3. And so the bond order is what? Which bond order? Carbon oxygen bond order is 1.33. It will be the same for all the carbon oxygen bonds. Like here you can apply, it is 1 plus, here you can apply, this is 2 plus 1 divided by 3 resonating forms. So it comes out to be 1.33 again. So it will be the same. So these are the some practical practice problems which you can practice, and this is up to the topic resonance. We can discuss about polarity of molecules now. The next topic of discussion is polarity of bonds. Why at all polarity develops in a bond? Actually, none of the bonds are perfectly covalent or perfectly ionic. In reality, no bond or compound is either completely covalent or ionic. In covalent bonds, there is some ionic character, and in ionic bond also there is some covalent character. When covalent bond is formed between two similar atoms, it is known as homoatomic molecules, AA type molecules. There is no electronegativity difference between them, and so the shared pair of electron is equally attracted by the two atoms. As a result, the electron cloud is located almost at the center of the two atoms, in center of the bond length of the two atoms. So here it is said, as a result, the electron pair is situated exactly between the two identical nuclei. Now, if I talk about, so these are known as non-polar covalent bond because there is no polarity difference. But if I talk about molecules which are of AB type, having electronegativity difference, we can assume that the electronegativity of B is greater than that of A. If we assume that, that means the electron cloud will be shifting little bit more towards B than that of A on account of greater electronegativity difference. Greater electronegativity of B. So B acquires a partial negative charge and A acquires a partial positive charge because the electron cloud is more towards B than towards A. That results in the shift of the electron pairs a little bit towards B and not remaining at the center, just like in the case of AA. So these types of bonds are known as polar covalent bonds, and that is developed on account of electronegativity difference of the two atoms. So as a result of this polarization, the molecule possesses dipole moment, which is defined as the product of the magnitude of the charge and the distance between the charges of positive and negative centers. Okay, so just as I said, it develops a delta negative charge, means slightly negative polarity and slightly positive polarity on the two ends. So the difference between the charges, the distance between the charges, that is taken as R, and Q is the charge. Mathematically, dipole moment is given as Q into T, Q into D, or Q into R. Whatever you write, it actually means product of charge into distance between the charges. And its unit is dBi. Unit is dBi, and the conversion factor is 1 dBi is equal to 3.33564 into 10 to the power of minus 30 coulomb meter. Now, this dipole moment is a vector quantity. Why? Because obviously the moment remains towards the more electronegative atom. So it is depicted by a small arrow with tail on the negative center and head pointing towards the positive center. So here we just write a dipole moment in this manner. So this is your bond moment because it is having only HF, two types of atoms. So it is known as bond moment. Okay. So this is the bond moment. Now, if I have more than one bonds in the molecule, okay, HF was having one bond. Suppose I have H2O. In case of H2O, what happens? It has a bent structure. The two OH bonds are oriented at an angle of 104.5 degree. So this is the 104.5 degree angle. Net dipole is something like this. It is the result of the dipole moment of the two OH bond. See, individually, if I see, this is the dipole moment. This is the bond moment. HO is the bond moment. Here again, HO is the bond moment. And this is your resultant dipole moment, which is a vector quantity. And this is charge into distance between the charges. Okay. So here it is how you have seen the dipole moment is represented. Now, dipole moment in case of BeF2 is 0. Why? Because the structure, the molecule is a linear molecule. BeF2. All these things will be clear why it is linear, why it is bent when we will do VSEPR theory again. But as of now, you consider that H2O has a bent structure. BeF2 has a linear structure, linear geometry, I will say, for which the individual bond moments, you see, they are oppositely directed, equal in magnitude but opposite in direction, for which the total dipole moment becomes 0 because it cancels each other's effect. Okay, so this is what is happening. Now, in tetraatomic molecule, tetraatomic means there are 4 atoms. See, B is 1 and 3 fluorine. So 4 atoms are there. So it is like A, B, 3 type of molecule. The dipole moment is 0. Although it is not linear, BF is oriented at an angle of 120 degree. Each angle is 120 degree over here. Each angle is 120 degree. But it is having a net sum of 0 dipole moment of the 3. The resultant is 0, for which BF3 molecule has 0 dipole moment and is considered to be non-polar. Now, one interesting fact is about NH3 and NF3 molecule. Both the molecules have pyramidal shape with a lone pair of electron on nitrogen. So if I say NH3, it will have NH3 molecule where nitrogen has 5 valence electron, 1, 2, 3 and another electron pair. It remains like this. And NF3 also, fluorine is occupying the place of hydrogen. So let us see the diagram over here, the pictorial representation. Resultant dipole of NH3 is greater than the resultant dipole of NF3, though fluorine is more electronegative than hydrogen because of the net dipole moment. In case of NH3, the NH bond dipole or bond moment is towards nitrogen, and in case of lone pair, it is towards the lone pair. and for which all the direction you see they are in the same side, and so the net dipole is additive in nature. It's a vector quantity. What is happening in NF3? Fluorine is more electronegative, and so the bond dipole or the bond moment is more towards fluorine, and in case of lone pair it is towards lone pair. So here there are 3 fluorine and there is 1 lone pair on the other side, for which this is the resultant dipole moment of NF3. So what happens is the resultant dipole moment actually gets reduced because on the other direction there is another bond moment. So the dipole moment of NH3 is greater than that of NF3. So here we can see that in case of NH3, the orbital dipole due to lone pair is in the same direction as the resultant dipole of the NH bond. Whereas in NF3, the orbital dipole is in a direction opposite to the resultant dipole moment of the 3NF bond. So what happens? The resultant decreases, for which low dipole moment of NF3 is seen. So this is what you have seen over here. Just as all covalent bonds have some partial ionic character, the ionic bonds also have some partial covalent character. And the partial covalent character is guided by a rule which is known as Fajan's rule. Okay, so what is the Fajan's rule? It says that if you have say a cation over here, say I'm talking about a cation, so I can say A plus or N plus and B minus or M minus. Okay, so this is an ionic bond because there is a cation and there is an anion. Now, this says that the power of the cation has a positive power. That means the nuclear force is exerted over the other anion which is next to it, the counter ion, for which there can be distortion of the electron cloud over B, which is the anion. Bm minus is the anion. So there occurs a distortion of the electron cloud that existed between the cation and the anion. So the power of the cation to cause this distortion is known as the polarizing power. The polarizing power is of the cation. That means the power to distort the electron cloud more towards itself. That means the electron cloud of the anion shifts towards the cation a bit, and it seems as if it is being shared between the anion and the cation. And for that reason, the ionic bond attains a covalent character. And the tendency or the ability of the anion to get distorted is known as polarizability. It is known as polarizability. This is the tendency of the anion to get distorted. So smaller the cation, size of the cation, greater and larger the size of the anion, greater is the covalent character of the ionic bond. How do we understand this? If the charge over the cation is greater, then only I will say the size of the cation is also small. So greater the charge on the cation, greater is the covalent character. Why is it so? Because if the size of the cation is less, then the nuclear force is greater and the polarizing power is greater, for which the electron cloud is shifted towards electron cloud of the anion is shifted little bit more towards the cation and is shared between the anion and cation, which we say as the covalent character of the ionic bond. Now for cations of the same size and charge, the one with electronic configuration N-1 DN-NS0, that is typical of transition metal, will have more polarizing power. Why? Because it has room. It has d orbitals empty and it can give room to the electron cloud. So it has a greater tendency to polarize the electron cloud over the anion. and it is greater than any other alkali metals or alkaline earth metals. The cation polarizes the anion, pulling the electronic charge towards itself and thereby increasing the electronic charge between the two. So that defines why the polarization occurs and why the covalent character occurs in the ionic bond. The polarizing power of the cation and the polarizability of the anion and the extent of distortion, that is the polarization of the anion, are the factors which determine percent of covalent character. This is another resource from which we can see some extra discussion. Common discussions we are not discussing, but you can go through the resource, of course. We have told about molecules which are having electronegativity difference, on account of which a polarity develops and we tell that it is a polar covalent bond. Ionic bond is an extreme case of polar covalent bond. Why? Because when the bond is so much so polar that electronegativity difference accounts, it gives rise to a partial positive charge and a partial negative charge, then ionic character acquires or rather develops in the covalent molecule also. So dipole moment, it is defined as the product of magnitude of charge and distance between the charges. Same thing, E into D, I have told you it is represented by D as well. So here it is D by is the unit. SI unit of dipole moment can be expressed in coulomb meter, which is D by. Okay, so it is also equal to, this is also very important, it is equal to 1 into 10 to the power of minus 18 ESU centimeter. Apart from how much coulomb meter, we should also know how much ESU centimeter it is. For example, the dipole moment of HCl is this much ESU centimeter, expressed as 1.03 d by. Okay, it's a vector quantity. We have seen the dipole moments of H2O, of CO2 linear, so a zero dipole moment, because the individual bond moment cancels each other's effect. Same thing we had seen in BeF2 molecule. Okay, so now let's see over here, BF3 we have already discussed, so we are not discussing that. NH3 and NF3 we have already discussed the same thing over here in the resource. So let us search for something extra, applications. Now here distinction between a polar and a non-polar molecule. So we can see if there is resultant dipole moment, then only we will say polar molecule, and if the resultant dipole moment does not remain, the dipole moment becomes zero, then it is a non-polar molecule. Polarity remaining means dipole moment value is greater than zero, means the molecule is polar in nature. Ionic character in a covalent molecule, how much of the ionic character it has? It's called percent ionic character. Now this percent ionic character is something like this, mu observed by mu ionic into 100. Okay, so let us calculate the percentage of ionic character in HCl molecules. Experimentally, it has been seen that dipole moment of HCl is 1.03 d by, and bond length is this much angstrom. Now for 100% ionic character, the charge developed on H and Cl atoms will be this ESU centimeter. So we have done the calculated one, ionic character, how much? It is charge into distance between the charges, and we have got some value. So this is experimental, this is calculated. So experimental by calculated into 100. This is the percent ionic character. Okay. Now shapes of molecules, we have told you that BeF2 has zero dipole moment, and so it is a linear molecule. Okay, or rather we can say that the molecule is linear, and so the bond moment cancels each other's effect. Similarly, water has a resultant dipole moment, so water molecule is not linear, it does not cancel each other's effect, it is bent or it has angular shape. So this is it. Now these are the some selected AB type having linear geometry. The dipole moments are given. AB2 type can be linear or bent. So like CO2 was a linear one. AB2 type is H2O also, but it is bent. Okay, it has two lone pairs. It is bent. AB3 type is this, AB4 type is this. Now problems related to percentionic character, this is one numerical related to the one which we have just now seen. You can access the material in the link clicking in the description part. Do access and practice the topic again and again. That's all for today. That's all for the topic. See you in the next topic, VSEPR theory. Thank you for being with me in this session. Hope to meet you in the next session with another topic.